Welcome to Brain Vision.
Our question says that assuming that the maximum displacement of the air molecules in a sound wave is about the same as that of a speaker cone that produces the sound, figure 44, estimate by how much a loudspeaker cone moves for a fairly loud 105 decibel sound of 8 kilohertz for A and B 35 hertz. So I wrote down some things that we were given both directly and indirectly. We know the decimal of the speaker is 105 decibels, right? That's how loud the sound is. So that's beta. Speed of sound in this medium, we're going to assume, is C sub S, is 343 meters per second. The intensity of the air is I0 is 10 to the minus 12 watts per meter squared. And then rho is 1.29 kilograms per meter squared is the density of the air, okay? So now that we know that, we need to find the intensity here. We're going to find the intensity that can be calculated from the decimal value, okay? So to calculate that intensity, we use the equation here, beta is equal to 10 times the log, which this is log base 10 here, log of the ratio of I, the intensity, divided by I0. Okay, so we want to solve for I, okay? Well, first thing we need to do is divide beta by 10 to get rid of the 10. So we have out front, we're going to have beta over 10, okay? But after we divide beta by 10, since it's log base 10, we have to raise both sides to the 10 power. So that beta divided by 10 is going to get raised to the 10 power to get rid of the log. So we have up top beta divided by 10, okay? And then multiplied by I naught to get the I by itself, okay? So we plug in these values. We have 10. Beta is 105 divided by 10 is 10.5. So this is 10 to the 10.5 multiplied by 10 to the minus 12 watts per meter squared. And we get an intensity of 0.0316 watts per meter squared. Okay, so now that we've found that, we can go ahead and use that to find the displacement amplitude, okay? So now we can find the displacement amplitude by using here, let me see what equation this is in the book, 15-7, okay? So that says that the intensity, so for part A, where we have a frequency of 8 kilohertz, which is 8 times 10 to the third hertz, we can use the equation I is equal to 2 pi squared times the speed of sound, C sub S, times the density of air, times the frequency we're considering, squared, times A squared is the displacement, okay? And we want to find A. So we can go ahead and rearrange this equation, solving for A. Okay. If we do that, we have 1 over pi f. Since the pi f are squared, the squares go away because we have to take square root to get A by itself. So we have 1 over pi f times the square root of I divided by 2 times the speed of sound times the density. Okay, so if you plug in, the constant pi that we always use, F for frequency here is 8 times 10 to the third hertz. I is what we found above, 0.0316 watts per meter squared. Speed of sound, 343 meters per second, and rho is 1.29. You plug all those in, and you find this equals 2.4 times 10 to the minus 7. This is meters. Okay, so box that in. That's our solution to A. Now for B, it says, what if we have a a frequency equal to 35 hertz. Okay, well, we're going to use the exact same equation as above. So you're going to have A is equal to the same thing, except for now we're going to have 35 hertz. So this is going to be pi. We'll just write it all out this time. 35 hertz multiplied by the square root. Oh, we don't need to put that because we'll have a square root here of I, which was 0.0316. Okay, divided by 2 times 343 meters per second times rho, which was 1.29 kilograms per meter squared. Okay. So if you plug that all into a calculator, find that this one equals 5.4 times 10 to the minus 5 meters. Box that in as our solution for part B.